Thank you very much. I'd like to thank the organizing committee very much for the opportunity to give this series of talks. I'm very excited about it because I've been working in actually representation theory and dynamics for quite a while. And I really do think that it's a subject that has a lot of potential, and it has a lot of possibilities. So I would like to present some of the progress that has been made and many questions that arise, which I think are quite interesting. I would like to start on a very leisurely note and explain a little bit of the history of ergodic theory. And as it turns out, it's quite remarkable that ergodic theory and ergodic theory and certainly ergodic theory and spectral theory had, you can almost say, a common origin, or maybe this is a little too strong, but they had a very significant point of intersection in their very beginning. So this is a very natural place to start. Okay, maybe we're going to skip the plan and we'll talk about it tomorrow. So we would like to begin by talking about averaging in dynamical systems. And I'd like to take you back to the origin of Hamiltonian mechanics. And a basic object of study in the context of classical Hamiltonian mechanics consists of a compact Riemannian manifold, the phase space, and a divergence-free vector field on it. So as we all know, the integral curves of the vector field V gives rise to a one-parameter group of volume-preserving transformations, AU from M to M, and U ranges over R, and this is called the time evolution in phase space. As you all know, this is the common underlying theme of the representation of a vast number of physical systems. And a natural question that arises is for a function f from the manifold to the real line, sometimes called an observable, one considers the time averages. Does this work? No. One considers the time averages along an orbit. Beta TFX is the integral of the observable f at the orbit points, AUX, taken from time 0 to time t, and we always consider the average of this quantity. And we would like to know whether these averages converge, and if so, what is their limit? And of course, there are many sub-questions to this general problem. You can view it for continuous functions in Lebesgue space, etc., etc. Now, from the beginning, it was clear that the following problem presents itself. So for a domain D in M, the fraction of the time in the interval 0 to t that the orbit spends in D is given by this integral of the characteristic function of D. The integral from 0 to t of chi d AUX, because chi d AUX is 0 if the point is not in D and 1 otherwise. And so a sub-question of the previous one is whether the visiting times converge to the volume of D. In other words, whether the orbit spends time in the set D in proportion to its volume when we normalize the volume to be 1. This has been a very important motivating problem. Now, clearly, when D is invariant under the flow, namely starting at a point x in D, the orbit AUX never leaves D, then this will not be the case. Okay, this is completely obvious. This is an obvious obstacle. It's an obvious obstruction. And so for the visiting times to converge to the volume, it is certainly necessary that invariant sets be null or co-null, so that they won't be observed measurably, shall we say. And flows satisfying this condition are called ergodic flows. So we can summarize this by saying that the flow has to be ergodic for the visiting times to converge to the right limit so that the orbit will spend the right amount of time in every set. And this brings us to the classical Boltzmann ergodic hypothesis, which is that for an ergodic flow, the time averages of an observable f converge to the space average of f on all of phase space, namely to the integral of f with respect to the volume. This is a very natural hypothesis, especially if you take into account the physical origin of this problem. And this ergodic hypothesis has been around for a very long time. It goes back, I think, to the end of the 19th century, or maybe the beginning of the 20th. And the answer to this hypothesis is given by the classical mean ergodic theorem, which I would like to consider now. So consider any probability space with a one-parameter flow of measure-preserving transformations AU from x to x. So each transformation AU preserves the measure. We are going to dispense with the structure of a Riemannian manifold and a divergence-free vector field. It's not really going to be relevant to abstract ergodic theory per se. This is a considerable generalization, but it's possible to deal with it directly. And then a key observation in the history of this subject is really simple, is that the operators f goes to f composed with AU, which we denote by pi x AU, are unitary operators on L2. And so that pi x AU, this collection, is a unitary group. Nowadays, it's really something that is, I think it's something that is really taken for granted. But this was an observation by Koopman in 1930. And actually, this observation has influenced von Neumann's approach to the mean ergodic theorem, which he proved in 1932. And in fact, von Neumann credits Koopman explicitly in his paper because von Neumann had this very good idea that he can prove the mean ergodic theorem which states that the time averages 1 over t, the integral from 0 to t of f ux du, converge to the space average, the integral of x f d mu, in L2 norm for any f in L2 if the flow is ergodic. So in particular, the Boltzmann hypothesis in the context that we discussed before. And von Neumann realized that he can utilize his recently established spectral theorem for unitary operators, for which he gave a proof only several years earlier. So this is a very important, I think, how shall I say, a very important lesson. You can see that the origin of certainly the mean ergodic theorem and some of the fundamental problems okay, so the origin of the mean ergodic theorem was tied to the foundations of spectral theory for unitary operators, and as we shall see later on, it would make a lot of sense to follow this lead and consider spectral theory for general groups or more general groups of unitary operators. However, it's quite strange that abstract ergodic theory actually followed a very different path. And what I would like to do now, I'm going to try to present to you a proof of the mean ergodic theorem, which is going to fit on one page, and it was given by Riesz in 1938, and it has no spectral theory in it at all. And Riesz's proof in 1938 is completely elementary, and really it's just a proof in linear algebra, you could say. Well, maybe linear algebra in a Hilbert space. So let H be a Hilbert space, and AU be a one-parameter unitary group, and let epsilon I be the projection on the space of invariants of all of these operators together. And then one can apply the averaging operators, the usual averaging operators, beta t, 1 over t, the integral from 0 to t of AU du. This is a convex average of unitary operators. So one can apply this averaging operator to a vector f of the form f equals ASH minus h. So I want to apply our averages to a difference, to vectors which are differences. But then, if you actually do this, then you get something very, very simple, because you apply beta t to the difference. And then all that happens is that this element AS shifts the interval of integration, right? And here in this difference you have a lot of cancellation. So really you're left only with the integral from 0 to s and the integral from t to t plus s. Everything else cancels. You take one interval from 0 to t and you shift it by s. So all you have is the two sort of boundary intervals, or whatever we should call them. Okay, so that means, that implies immediately that the norm of the function beta tf is bounded by 2s over t, the norm of h. This follows from the absolutely most obvious estimate. You simply take the norm, and it's just because the measure is small, this measure. This is how you get this inequality. And of course, this converges to 0 as t goes to infinity. Now, in addition, 0 is in fact the projection of f on the invariants, because it's very clear that if f is a difference, then it will be orthogonal to every invariant function. And so we see here that if f is indeed a difference, then beta tf converges to the projection of f on the space of invariants in this case. Okay, so to conclude the proof that beta tf converges to the projection for every f, one first notes that if f is invariant, there is nothing to prove. Then beta tf equals f equals the projection for all t. That's an obvious case. So now we have two subspaces. One is the subspace which is spanned by all the differences. And the other subspace is the space of invariants. And the end of the proof is to say that the sum of these two spaces is everything. And then you have the mean ergodic theorem. And so finally, one shows that the span of ASH minus h, where s is an arbitrary point in R and h is in the Hilbert space, is dense in the orthogonal complement of the space of invariants. And this is a one-line exercise in linear algebra where you have to use the obvious properties of the bilinear, the Hilbert product, the bilinear form. And so what you have here is a complete proof of the mean ergodic theorem for unitary groups. In particular, it's actually even more general than that. So clearly, this is a very good proof. And this proof had enormous influence in ergodic theory. And of course, everybody can realize that the key here is, the key to this idea is right here, in this idea of shifting and canceling, basically. So this proof was utilized, and we will get to this in a moment. But I'd like to mention in passing that von Neumann was interested not only in averaging in dynamical systems, but also he was interested in averaging on groups or semigroups. And the classical example of such averages is a Banach limit, namely a non-negative linear functional on bounded sequences on the integers, which assigns to a bounded sequence and its shift the same value and agrees with the limit for convergent sequences. So this goes back even before to Banach and his circle. And von Neumann in 1940 considered groups which admit a right invariant mean, namely a translation invariant non-negative linear functional on bounded functions normalized so that m of the constant function 1 is 1. And von Neumann called these groups meanable groups in his original paper, in his original notes, or lectures, I think they were. Sorry?
In 1929, he already introduced notion of amenable groups.
Yeah, I'm referring to his well, book, I would say.
In this case. Because Bakulibo in 1939
Yeah.
considered this notion for topological groups and proved the existence of invariant measure.
Yeah. Well, I'm referring to the book von Neumann wrote in 1940 on his in his lectures. But I'm not sure I'm aware of the, I'm not aware of the reference that you cite. You say that he defined it already in 29?
Yes,
but
in case of discrete groups. While in 1939, Bakulibo considered topological
Okay.
groups with
Okay, well, thanks. I'm going to take this reference.
In the context of Krylov-Bogoliubov theory, what
Okay.
later is Krylov.
Well, that's coming up in a minute. Yeah, well, I guess the reference there is not so correct either, but I mean the date. But okay, well, I'm going to take this reference after the talk, but I assume it's in German or not.
It's in what?
It's in German for von Neumann and in Ukrainian for Bogoliubov.
Okay. Okay, so von Neumann established this class as a common generalization of compact groups and abelian groups by proving the existence of Haar measure for compact groups and the existence of invariant means or Banach limits for general abelian groups in these talks. Now, as I said before, the crucial property of the intervals 0t and r in Ries's proof is that they are asymptotically invariant under translation. Von Neumann's construction was an invariant mean, a mean which is invariant under translation. And in Ries's proof, the most significant issue was the fact that the intervals were asymptotically invariant under translation. As you translate, the effect of the translation becomes less and less meaningful. And that means that the measure of the symmetric difference 0t, symmetric difference with 0t plus s divided by the measure of 0t converges to 0 for any fixed s. And given any LCSC group G, Fallner defined a sequence of sets Fn of positive finite measure to be asymptotically invariant under right translation. If it satisfies for any fixed G the same asymptotic invariance condition. Fn G translated by G symmetric difference with Fn divided by Fn converges to 0 as n goes to infinity.
And I allow myself to remind, for somebody who may be not familiar with terminologies, that LC means locally compact second countable. Right?
Ah, yes, thank you very much. LCSC, locally compact second countable, thank you very much. And Fowler showed that the existence of an asymptotically invariant sequence is equivalent to the existence of an invariant mean. So the asymptotic invariance can be turned into invariance, and conversely, given an invariant mean, it can be approximated by an asymptotically invariant sequence. This was the gist of Fowler's argument. And so it characterizes meanable groups, which somehow subsequently were renamed amenable groups. So it's kind of curious, but in terms of terminology, meanable and amenable are really equivalent. I don't know. Okay. So a straightforward application of Ries's argument shows that an asymptotically invariant sequence satisfies that the uniform averages beta n on the sets Fn converge to the projection on the space of invariant. And this is really just an elementary exercise. If you take the argument that Ries presented for the real line and you replace beta t everywhere by beta n, the proof will be exactly the same. So this is definitely a big success of this proof. And therefore, we can conclude that amenable groups satisfy the mean ergodic theorem. And the main focus of ergodic theory has traditionally been on amenable groups, and asymptotically invariant sequences played a crucial role in many of the arguments. And I think that the success of these arguments played a big role in this, I mean, of the argument that we've already seen. And we will briefly mention some of the results that depend on asymptotic invariance, but first, let us introduce the general setup of ergodic theorems and the averaging operators, which will be our main subject below. So we're going to have a very straightforward generalization of the classical ergodic averages. G is an LCSC, i.e. locally compact second countable group with left Haar measure, let's say, Mg. Bt will be a growing family of sets of positive finite measure. Beta t, the Haar uniform averages supported on Bt, namely we take the characteristic function of the set Bt and we normalize it by the size, by the measure. And x mu is going to be an ergodic probability measure preserving action of G, as we had before. And the basic problem is to study the averaging operators pi x beta t. Fx is the average of f, once again, on the orbit, the g orbit of x. We sample the values of f on the g orbit of x on the set of translates bt, and then we take the average. And we would like to study the convergence properties of these operators. And now, asymptotic invariance of a family or a sequence Bn played a crucial role in the following. It played a crucial role in many other arguments, but I'm highlighting the following three arguments. One is the fact that pointwise convergence of pointwise convergence of pi x beta n on a dense subspace of L1. If you think about it for a moment, you can use the same Ries argument that we've presented to show this fact, because if it's a dense subspace, one can consider differences and differences and invariants, and we know that this spans a dense subspace. And this fact, pointwise convergence on a dense subspace, is used heavily in the proof of pointwise ergodic theorems. Pointwise ergodic theorems are those ergodic theorems in which you state a stronger conclusion than von Neumann's, namely that the operators converge almost surely. And it appeared certainly in Wiener's proof of the ergodic theorem, Calderon's version of the ergodic theorem, Temperman, Emerson Greenleaf, and many others. Another very important point that will make another appearance a little bit later on is the transference principle, which reduces the maximal inequality for the operators pi x beta t in a general action, in a completely general action x, to the maximal inequality for the convolution operators rg beta t in the regular action of the group on itself by translation. And this was noted already by Wiener and Calderon. Hertz had a version of the transference principle. The name transference was coined by Guido Weiss in this case. Koifman Weiss, I think in the paper of Koifman and Weiss in 1974. So this is a very heavily used principle in amenable ergodic theory, that the technical but very crucial tool of a maximal inequality in a general action can be reduced to the same maximal inequality for convolutions, namely in the regular representation. And finally, another crucial fact is the existence of invariant measures for continuous action on a compact metric space and the resulting theory of equidistribution, but I guess I have to change the reference by 11 years, you're saying?
They started in around 1930. The most famous result that for single transformation there is invariant measure.
That's already from 1930?
There was many other articles.
Oh, wow. Okay, so, okay.
So by 20 years.
20 years, okay. Okay, thank you very much. Anyway, these are three very substantial facts.
They were writing in French.
Sorry?
They were writing in French.
There may notice, I think, in French and maybe even in the Annals of Maths or something like this, actually, in some Western, because it was, in fact,
No, but this was much later.
No, but in 1950 it was no longer possible to publish in Western journals. But their references,
Okay.
their references in a Western journal, if not annals, then something similar.
Well, if I'll have internet, I'll try
so it's
to...
easy to check. This is easily verified. Yes,
Okay.
yes. So it's not possible. Yes.
Okay. Okay, in any case, we have here three very substantial principles, and this really shows why, and they really depend crucially on asymptotic invariance, but really, okay. So it explains why this has been such a crucial ingredient. But in some sense, what I would like to say now is that I'm going to discuss another consequence of asymptotic invariance. The point now is going to be that asymptotic invariance really appear as a big constraint. Because what asymptotic invariance does is that it allows a very flexible construction of almost invariants in various spaces. And that appears in a constraint in the following way. So another consequence of the existence of asymptotically invariant sequence in an amenable group is the following. In every properly ergodic action of G on a probability space X, there exists an asymptotically invariant sequence of unit vectors, Fk. So Fk are functions in L2 naught, namely they have zero mean, their integral is zero, and they're asymptotically invariant in the sense that pi xg Fk minus Fk, the norm converges to zero for all G in G. This is a condition which is very reminiscent of what we saw earlier with Fallner sets. And so you can see that asymptotically the function Fk remains almost invariant. Pi x G Fk is really almost Fk. They have very small difference in norm. And For countable groups, this property is equivalent to the existence of small asymptotically invariant sequence of sets in X. And in fact, it characterizes countable amenable groups. It's precisely those groups that have these sequence of asymptotically invariant sets in every properly ergodic action. This is due to Del Junco and Rosenblatt in 79 and Schmidt in 81. And from what I've said so far, this probably doesn't seem surprising at all. You have asymptotically invariant Fellner sets in G, and you can use them to construct various asymptotic invariants, for example, inside a probability measure space.
But what is small asymptotically invariant?
It's a sequence of sets such that GAN delta AN divided by the measure of AN. Okay. GAN delta AN converges to 0 for all G, and of course it has to be non-trivial, so it has to be sets which are not very close to everything.
So small stay here for this 0.
Yeah, they have to have a bound on their size. No, it refers to the size of AN. For example, they actually showed, they showed that this is possible to realize, or maybe more simply, we want a sequence like this such that mu AN equals 1/2, all of them. This is, I think, sometimes referred to as an I sequence by Schmidt.
I think small, they use this terminology without small.
Sorry?
Asymptotically invariant sequence.
Okay. They also showed that you have a sequence like that for any given.
Yeah, but, so in condition there is the beginning of separation of measures like from 0 and 1.
Okay.
And equivalently, you can emphasize it's equal to 1/2.
Okay. Okay, so the conclusion we want to draw from this is that when G is amenable, all averaging operators satisfy that their norm in the space of zero mean functions is equal to 1 in every properly ergodic action. This is a very simple exercise. It's a very simple exercise given an asymptotically invariant sequence of unit vectors to average them on beta and show that the norm of beta cannot be less than 1. And similarly, let's stick with asymptotically invariant sequence. If one averages this equation over beta, then one obtained this conclusion. I want to emphasize that the interesting conclusion here is when you take the set of mean zero functions. Without this condition, it's obvious, if you look at the constant function, that the norm is 1. This is a complete triviality. It's not a trivial fact that the norm in every properly ergodic action is 1, and it follows from this property. And by this characterization of Del Junco and Rosenblatt and Schmidt, one corollary of this is that in properly ergodic actions of amenable groups, no rate of convergence to the ergodic mean can be established in the operator norm. This has a very simple bottom line, and the bottom line is if you have an amenable group and you take any measure on it whatsoever, any probability measure on it, and you have a properly ergodic action, the norm in L2 is going to be exactly 1. So there's really no room.
I understood. I don't understand. What does it mean, properly ergodic action?
Properly ergodic is non-transitive. Ergodic, but not transitive.
And what do you mean by transitive?
Well, I mean, first, for countable groups, you can consider finite actions. These are legitimate ergodic actions. For locally compact groups, you have a large collection, often, of probability spaces with a transitive action.
The way voluble is called transitive for ergodic.
Transitive?
Yes, instead of ergodic, but it's. But okay,
Yeah.
transitive, you mean just when orbit is identified?
I mean that there is an orbit of measure 1.
Ah, there is an orbit of measure 1, of course, of course. That's right.
Yeah. Yeah, transitive and ergodic are sometimes. I never. I mean, I make a very strong distinction between them, but of course, transitive and ergodic has been used as a synonyms in some. Yeah, but I mean really transitive, namely there is an orbit with measure 1. Everything else
It's
doesn't
properly
exist.
ergodic.
Yeah,
If it does not exist, we say it's properly ergodic.
properly ergodic.
Honestly ergodic.
Yeah, honestly ergodic. Maybe this is a better. Okay. Okay, so we are done with the quest, if we are interested in it, of establishing any rate of convergence in the amenable world. But you can see that this is really tied into the reason why these averaging processes are so successful. It's possible to use asymptotic invariance in G to construct asymptotic invariance in X, so the conclusion is all norms are 1. Okay, so now we would like to go over to non-amenable groups and spectral estimates, and of course we can conclude from the characterization that when G is non-amenable, at least in some ergodic actions, at least some of the averaging operators pi x beta are strict contractions on L2 naught, of course. And so it is natural to go back to von Neumann's original approach and prove ergodic theorems via spectral methods and operator theory. And that's the plan for the next, that's going to be the plan from now on. And I would like to say that already the simplest conclusion is useful in many situations. If pi x beta is a strict contraction, so that pi x beta L2 naught is equal to alpha, which is strictly less than 1, then the powers pi x beta to the power k, which is the same thing as pi x beta convolved with itself k times, well, they satisfy an ergodic theorem of sorts, namely pi x beta convolved k times minus the integral. Well, it has exponential decay to 0. This is a complete triviality as a consequence of the fact that pi x beta is less than 1, but nevertheless, this is an equation that has a lot of content, or inequality that has a lot of content. Sorry? Yes, I'm sorry. There should be, of course, the norm of f here. So.
But also 1f.
Yes. Yes, okay, I'm sorry. There is an f here, and there is a norm f here. I'm sorry about this. Okay. So I'm not going to, okay, so this is an equation, of course, that everybody who has ever considered, let's say, a random walk with governed by beta on a certain space X is very interested in, and it's a very useful inequality. It has a lot of applications. But what we would like to do now is turn to a systematic study of averaging operators which are strict contractions. And a large part of what we would like to do is to generalize this inequality. Okay. So, so basically, we have a strict contraction, and strict contraction is usually also goes under the name of a spectral gap. So we'll start with a definition. An ergodic G action has a spectral gap in L2x if one of the following two equivalent conditions hold. The first is that there does not exist a sequence of functions with zero mean and unit L2 norm, which are asymptotically G invariant, namely for every G in G, pi x gfk minus fa converges in norm to 0. So that's the contrapositive of what we had before. And the second condition is that for every absolutely continuous symmetric generating probability measure beta on G, pi x beta f minus the integral of f d mu is less than 1 minus eta times the norm of f for all f in L2 and for a fixed eta which is strictly greater than 0. Namely, it's equivalent that there will be no asymptotically G invariant sequence and that many measures, good measures on G will be strict contractions. And here generating means that, for example, that the support of beta star, beta adjoint star, beta generates G as a semigroup, but there are many other conditions which guarantee that. That's just one condition.
So the point of the second condition is that eta does not depend on the action.
No, I didn't say that. I didn't say that, and usually eta does depend on the action. Yes, typically yes. It's a spectral gap for x. It's not a spectral gap beyond it. Yeah. Okay, but what I'm saying is that, well, I mean, for us, the most interesting part is going to be that this condition of absence of asymptotically invariant sequence implies that we have a very large collection of spectral estimates. What are these spectral estimates? These spectral estimates are that a lot of measures on G, those measures which are generating in a suitable sense, are strict contractions. Okay. Now, let's note, however, that the spectral gap assumption implies only that pi x beta t in L2 naught is strictly less than 1 for each t separately when beta t is generated. The only thing you get from a spectral gap is the inequality that you're less than 1. But the natural applications in dynamics require understanding the behavior of a family of averaging operators pi x beta t where mg beta t goes to infinity as t goes to infinity. And I'm sure this is obvious to everybody at this point, right? We have an average, we make it larger and larger, and we expect it to converge to the average on the space average. It's not so interesting to know that one particular beta t has norm less than 1. But remarkably, this problem is completely open, and I would like to call attention to it. I think there is a very interesting large collection of open problems here for those of you who are interested. And let us demonstrate it more directly. So let gamma be countable, and let d be a left invariant distance, and bn the balls of radius n and center e with respect to d. And let beta n be the uniform measures on bn. So we're still in our usual context. We've now taken a countable group, and we have some balls with respect to some metric, which is natural.
We assume the balls are finite.
Yes, we do. Sorry? Yes, okay. We definitely assume the balls are finite, yes. Yeah, yeah, okay. I'll say something about this in a minute, about the generality here. So let x mu be an ergodic action of gamma with a spectral gap, and assume that beta 1 is generating, so that you know that the norm pi x beta 1 in L2 naught is strictly less than 1. And the question is, what do you know about the norms of beta n? And so the first problem is to show that pi x beta n in L2 naught converges to 0. And as far as I know, this problem is completely open except for a very small number of cases, which I will say something about a little bit later on, maybe tomorrow.
And you expect it to be true in this?
Well, in this generality, for example, a good place to start would be to take D to be a word metric on a finitely generated group. As far as I know, this problem is completely open.
Maybe this was never spoken yet of the pi x is Putman representation.
Yes, yes.
And beta n you consider as element of group algebra.
Yes.
Because usually Putman representation is applicable to group to elements of the group or group algebra.
Yes. I'm not sure. So what's the question?
No, just
Okay.
understanding the problem.
Okay. Well, the problem is you have a convex average of unitary operator, which is given by the uniform measure on beta 1 or beta n. And there, okay, in this generality, this is, I don't know, I mean, it's really very general. In fact, it applies to all non-amenable, let's say, non-amenable finitely generated groups. But it's a very striking fact that so little is known about it. And in fact, problem 2 calls for a lot more, which is to show that if you have a spectral gap for beta 1, then in fact pi x beta n in L2 not converge to 0 exponentially. This is certainly true in certain situations, but in general it's completely open. And the reason why one should think of it as a reasonable problem, well, I don't know about the reason why this should be plausible is that typically we think that if we have a certain growth, a certain filtering of the group, let's say by balls of a word metric, and we average the functions in L2 naught and we got a strict contraction in beta 1, then if we do it with beta 2, somehow the contraction is even greater. So it feels like a heuristic, a reasonable heuristic, but as far as I know, this problem is completely open. There are examples for certain groups where one can actually establish this, but these examples are very particular, and they all depend, I should say right now, they all depend on very, very detailed spectral theory. The point in this would be to have a much more general semi-geometric argument that starts with a certain level of contraction and produces more contraction. Okay, so a most remarkable class of non-amenable groups was unveiled by Kazhdan in 1967. And so we will give the original definition of Kazhdan or something close to it tomorrow, but in our discussion here, we will say that G has property T if and only if every ergodic action has a spectral gap. And the equivalence of this definition to the original definition was proved by Kohn and Benji Weiss this time, and Schmidt in '81. And in fact, an even more remarkable property holds, namely the following strong uniform estimate. G has property T if and only if for every absolutely continuous generating measure beta, there is a fixed alpha beta strictly less than 1, such that in every ergodic action of G on X, the following uniform operator norm estimate holds. This norm is less than alpha for all ergodic actions without any exception. So it's a completely uniform estimate on the norms of these averaging operators. Okay. And let me mention very, very briefly that the possibility of ergodic theorems with rate of convergence for actions of the free group with a spectral gap was first realized by the Lubotsky-Philip-Sarnak construction of a dense free group of isometries of S2 which has an optimal spectral gap. That has been a very influential construction.
But optimal in what sense?
Optimal, we'll talk about optimality a lot, so let me wait a little bit. For groups acting simply transitively on the vertices of an A2 tilde building, Cartwright, Mlotowski, and Steger have established property T directly and computed the norms of natural averages on the group explicitly. As a consequence, one can obtain an effective ergodic theorem for these averages in general ergodic actions of the group. And for higher rank connected simple Lie groups with finite center, the effective pointwise ergodic theorem for radial averages was established in joint work with Margulis and Stein. Now, in the last 3 minutes that I have, I would like to formulate, though, a result which should be compared to what we started with, namely an effective ergodic theorem for lattice subgroups. So we take G to be a connected semi-simple Lie group with finite center and no compact factors. For example, SLN R or SON1. S equals G mod K is the symmetric space, namely unimodular, positive definite symmetric matrices or hyperbolic space. BT are the Riemannian balls in symmetric space lifted to G. D is the G-invariant distance function associated with a killing form. This is really very important in what I'm going to say in a moment. And gamma is any lattice subgroup, for example, SLNZ or fundamental groups of finite volumes, hyperbolic manifolds, etc. And lambda T are the uniform measures on the intersection of gamma and BT. Yes? A lattice is a discrete subgroup, gamma, such that G mod gamma has finite invariant measure. The volume. The most obvious example are the integer lattice ZD in RD. So lambda T, we take the finite discrete set of points gamma intersect BT and we call it gamma T. And now, if the gamma action has a spectral gap, then the effective mean ergodic theorem holds. For every f in LP, the LP norm of lambda TF minus the integral of x of f d mu converges to 0, and in fact, it converges at a rate which is a negative power of the volume MBT. Where theta p depends on the action. And under this condition, the effective pointwise ergodic theorem holds. For every f in LP, lambda tfx minus the space average converges to 0 once again, and we have a fixed rate, which is a negative power of the volume of BT, where theta p is a function of x. And I would like to emphasize that this result holds for all gamma actions. The only connection to the original embedding of gamma in the group G is in the definition of the sets gamma t. So, for example, for these distances, the two problems that I've mentioned 5 minutes ago have a positive solution. They're not word metrics in any way. But in this case, you have exponential decay of the operator norm. Okay, so we're going to continue to discuss this tomorrow. Thank you very much for your patience.
Thank you very much.